Do you guys? So this is called the Blackfeet Nation. So what's this line called? The border? I thought it was called the medicine line. Anyway, so we're here. It's 1.5 million acres. That's a lot of country, and I understand that it's not as big as your actual homeland, right? Which I understand went down to the Yellowstone and then way up into Canada, and I mean, that's where the rest of the Confederacy is, right? I'm not teaching you guys anything new, but who knows Pecani? Oh, you do?
That's where I'm from, yeah.
Oh, bummer. Okay, so don't make fun of my pronunciation, okay? Hey, Jalen, can you give me a ride out to Mission Lake later? Or are you busy all afternoon?
Well, I could leave him over there and bring you out afterwards.
Do you mind? Cool. So what's happening here, you guys met them all yesterday, is we're up here with an MSU crew. I'm from Montana State University. I teach soils there. I try to teach soils there. So I've got a bunch of workers. They're out in the parking lot making lunch, and they came in because we tried to use the Connie Lodge van, and it didn't really work out. So the reason that I'm here is that the Pecani Lodge Health Institute, we partnered with them, Montana State University, and we got some nice grants from the U.S. Department of Agriculture. And so the one that is paying for me to be here right now is called Grazing for Soil Health. And then I'm going to start with just thinking a little bit about this word. Is the font size okay? Everything good? What was your name, sir?
Oh, Austin.
Austin, thanks for doing this. Let's just go down the line. You ready? Jaden, what's health? Remember, you're not mic'd up, so I'm going to have to repeat it for the purposes of recording.
Health is something wellness.
Is it wellness?
Oh my gosh, that's incredible. Well, and the reason that I really like your vote on wellness, or some people call it well-being, is that that's actually the same definition that this crazy group called World Health Organization uses. And I thought I would just read it to you guys because, I mean, I Google it every year. You would think I would have memorized it by now, but I'm not good at memorizing things. I'm terrible at learning names. Actually, what's your name? You look like you are Maverick. Like the movie?
Like the movie.
Dude, and then Rio?
Yeah.
Wow, are you Portuguese?
No.
That's interesting. Great names there. So Rio, Maverick, I know everybody else. So here's what the World Health Organization calls health. A state of complete, not partial, complete physical, mental, and social well-being, your word, beautiful, and not merely the absence of disease or infirmity. So what's really interesting to me is that there's this crazy international group called the World Health Organization, and what they're saying is, hey, it's just not about not being sick. So raise your hand if you're sick. So no one's sick? Jalen? What happened to your hand? Oh, no, I'm just saying, like, I heard a rumor that, something bad had happened to your hand. Anyway, the really big deal is that, does everybody get how health can be aspirational? She's giving me the finger. It's really funny back there. She was like, oh, no, I'm just raising my hand. I'm like, oh, that's really interesting because your middle finger was up. No, I'm just kidding. So understand that this is aspirational. And then the title of this is supposed to be, and I really want to get us walking so that you guys can see the transect again, especially Rio and Maverick, because this is supposed to be 100% outside. So the reason that I really want to emphasize that we're in a U.S. Department of Agriculture funded grant with Pecani Lodge. It's called Grazing for Soil Health, and then you could say, oh, how do you measure soil health across 1.5 million acres? I think the thing that I really want to emphasize here is that this is aspirational, right? It's a complete state of physical, mental, and social well-being, and it's not just the absence of poor Jalen's infirmities or whatever, okay? And then I can tell you that this whole session was supposed to be called How Do We Measure Soil Health? it's such a large scale, and I can tell you really honestly, you guys got a little preview of this yesterday. Well, we don't know how. So Montana State University doesn't know exactly how, but I'm going to show you some ideas that Western science brings to the table. You're going to appreciate it a lot more outside. And then I'm going to give you a couple numbers. That's why I brought some of these things in with us today. And then I also, Maverick speaks Pekani, but I'm going to sort of teach you like sort of the main idea. And the nice thing is I'm going to leave this whiteboard here because I'm going to do a lot of all my whiteboard stuff right now. So the really big deal is that, Browning's like right there. I have no idea. And then when we walk outside, what you're going to see is a hill slope that sort of looks like this. So down here, we could call this Depot Creek. And I don't know if you know this, but like, I don't even know how to draw, but this is going to be a beaver with a big tail. And, they're beaver on Depot Creek. But the important reason that we're talking about this right now is that we have dug some holes, and here we could call it like the crest. It's like a little hilltop. And I'll talk about what the numbers are in here. And then we actually went to a place that some people, we were just arguing about this morning out by Mission Lake, some people might call this the shoulder. And that just means another position where we can dig a pit in the soil because we are going to talk about soil health. And then we have another one, shoulder in here. We're going to call this the shrub site. And then this is really funny, but down here we dug a pit, and down here we dug a pit, and this one is now covered. So they put in like a foot of gravel because this turned into a building site. And that sometimes happens. We dig holes in the ground and then we don't really clear it with the powers that be at Blackfeet Community College. And as a consequence, they came in, and you'll see this when we go outside. There's a whole bunch of gravel out there. And so I just wanted to share what these numbers look like. So one of the things that we measure in the soils, all of you guys are really good at it, especially digging through rock, we learned that yesterday, is we can measure something in the soil called soil organic matter. And the way we do that is we take a little sample, and the sample could look like this one, which I will pass around. And Maverick, if you could just hand that on back, that'd be awesome. So we would take that sample and we would grind it up and what we call homogenize it. We stick it into a furnace and we can measure really, really precisely how much organic matter. And the numbers that I'm going to read you right now range between 1 and 38%. So those are from these 5 positions that we've done at BCC. From 1, sorry, that doesn't show up. Austin, you yell at me if I'm doing something wrong. From 1 to 38%. So, we could call that almost 40%. But the other thing that we do for every single one of these layers that we'll see in the soil today is we also do the rock. And then the last thing that we do is something called the bulk density. Anyway, the big deal, guys, is that we can take each of these 3 numbers, and when you multiply them together, it's a little bit of magic. I'll put this in red because I'm going to try to get out of here in 10 minutes. I don't know if I can do it. These are the numbers that we get. Oh, guess which one has the most carbon? Rio, what's your guess? This one. Okay, I'm going to put a little vote for Rio, and he gets a red X because that's not right. Okay, Maverick. Remember, we're asking where is most of the carbon, or that's another way of saying organic matter. The one sample that's going around, where's my dirt clod? Right there. That's probably 90% organic matter or 45% carbon, right? It's super light because when you fluff things up, or I'll give you a Pekani word for it in a second, gooey. When things turn gooey, like a spongy, like a wetland, it has a lot of organic matter. So Maverick, what was your guess? Top. Oh, going big. Okay, so Maverick votes crest. He also gets a red X. Okay, who's feeling good? Caden, what's your guess? Shrubs. And that's because you peeked and you saw all that organic matter at the top. And Caden says, oh yeah, I saw this yesterday, and the high 38% organic matter goes with the shrub. Caden voted shrub, but guess what? Caden gets a big red X. Okay, Kelsey, it's a 50-50. We call this the floodplain or the shoulder. Which one? Yes, this one has the most, right? So Kelsey, for the win, you can go in blue. I'm just going to do 2 letters. So it turns out Kelsey's right, and the floodplain has about 100 tons of carbon in 1 acre to 1 foot depth. And this is how we abbreviate it, is we use language like this. We say, what is the mass? How much does something weigh? 100 tons per acre foot, like this one, big check mark, or we'll give you a little star. Okay, so that's an excellent, excellent guess. And it turns out, like you guys, starting with Rio, not too far off. And it actually is really, really smart that you were thinking that it was the highest amount of organic matter, but there's only 30. And then Caden voted at the very tippy top, which we will go visit. It's only a short walk out there. There's only 55. And then the shoulder has 34. And Caden voted the shrub because he saw all that organic matter, but that one only has 45. So unfortunately, like the winning place that had the most organic matter, another way to think about that is carbon, which we abbreviate with the capital letter C, is now underneath a bunch of gravel, and so I can't show it to you. But when we go out there and we're looking at the transect, you'll be able to see like that's the place that has the most carbon. Why are we interested in carbon? Any ideas? Some of the interns. Leslie, what was your guess? Carbon. Oh, that's right, because you're made of carbon. Like your fingernails, your eyeballs, your hair, your skin, it's all carbon. I mean, you are a bag of water. All of us are bags of water. We're born as bags of water, but then we dry out. Like the older you are, the drier you are. It's kind of gross. Like I'm like 50% water because I'm really old, but you guys are really, really young. Anyway, that's one of the reasons that we care about carbon. But the other one is this. Like if this is a different kind of hill slope and we look at this as sort of, this is land and then these are oceans. It turns out, I don't know if you guys can see this or do I have to do it higher? JR, can you see this? It turns out that every year land pops out 120 billion tons of carbon, and then the oceans also are pumping out 80 billion tons, right? So I've got slightly different units than this. This is just a ton of carbon, but I'm saying you have to add 9 zeros and then you have tons of carbon. So this is the world. This is not Blackfeet Community College. This is the whole world. I'm really curious. We're going to go around and just do a vote. So if this is a house and these are humans, right? So here's all of the interns with their shovels. And they're really excited to dig, which I love. I want you to guess at how much carbon, like, so we drove, right? You guys have met the ski van. Maybe all of you drove here. Like, how much do all of those cars and planes and automobiles, like, how much carbon is related to all those? And before I tell you that, if we go back 200 years ago, the oceans were also pulling in a bunch of carbon. We're going to talk about like why that is. Oh my gosh, and I know I drew these numbers really small, but land was also pulling carbon out of the atmosphere, okay? A little trick is that, and this is what I was reading in your thought bubble, Leslie, besides the fact that your fingernails are made of, so carbon is a piece of what we call carbon dioxide, and I'll talk about this because I have a Pakani word for it, and please, Maverick, just say, yo. You have bad information, which is great. So when you have carbon dioxide in the atmosphere, like this room can have probably, you guys are really fancy in modern building. I teach in old classrooms, but I bet you there's, I've been talking a lot, maybe 1,000 parts per million. So outside of this room, there's 420 parts per million. And what happens is that when the sun is out, plants photosynthesize. So this arrow is really photosynthesis. And then this arrow is also photosynthesis. Okay, so now that I've learned your names, we're all going to go around, and we will not be alphabetical. Rio's going to go first, then Maverick, then Jalen, then Leslie, then Jaden, the other Jaden, and then Jalen, Jaden, like that's so hard, JR, keep me going here, Caden, Kelsey, and then Chase, and then Tucker, and then Austin. Look at that. Oh, this is going to be a great vote. So what you're voting on, does everybody understand? Like I just gave you how much the land exchanges with the atmosphere in tons of carbon, but with 9 zeros because it's billions of tons, billions. And billions is this in the United States. It's something else in England, but billion means 9 zeros. And again, this is 80 billion tons every year of carbon out of the ocean because the oceans are breathing. But then there's little guys in here called phytoplankton, and they're basically photosynthesizing in the ocean. And by the way, there's lots of ocean, right? So let's go, Rio. Just put a number into this arrow. Does everybody understand? Like outside, there's a ski van. You can't see it. It has a little exhaust pipe. And so you all know that what mostly comes out of the exhaust pipe. Like it's a diesel, right? So it's mostly carbon monoxide, so you should never be breathing like what the diesel van is emitting, but it's also producing carbon dioxide. All these things are producing carbon dioxide. What is that number, Rio?
40.
Oh, good one. Maverick?
1,000.
1,000, going big. Jalen?
1,500.
Woo! Leslie?
500.
Okay, a little modest. Jaden? 6,000 for the win! Boom, star. Okay, JR? 6,002? Okay. Caden?
5,000.
He doesn't believe me that I'm getting excited. Maybe that doesn't get a star. Kelsey?
2,000.
Tucker? Dude, don't overthink it.
10,000.
10,000. Okay, Austin, bring us home.
A mil.
Wow, okay. So it turns out the reason that we got this project called Grazing for Soil Health is I'm trying to teach you guys the carbon cycle in 6 arrows, right? 80 out, 80 in, right? So, 80 out of the atmosphere, 80 into the atmosphere. So guess what? 80 minus 80 is 0. And so these things, 80 and 120, so 120 minus 120 is 0. Like this is what the world looked like 200 years ago, before humans figured out how to burn fossil fuels over here. So all of you guys, don't take this personally, but here, can I grade you guys? X, 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 X. Rio was closest, so you get a handshake. But the right answer is 12. And I'm going to tell you why that's important. Like this arrow is 12. All humans, with all of our food and all of our gas and all of our buildings, we only generate 12 billion tons of carbon a year. Can you see that that's a really small arrow, even though we got Austin to vote 1 million for the big win? Like that's a really small arrow compared to how much plants are producing, right? Especially 200 years ago. These numbers are updated. These are from like 2 years ago. But the oceans, I mean, I just want you to see that all the oceans are exchanging more carbon than all of our planes, trains, automobiles, and food, okay? The reason I talk about this in 6 arrows is that this arrow is also human. And it gets a big question mark because we don't know how much carbon we can pull out of the atmosphere within things like improved grazing practices. Does that make sense? Like, does everybody get that if we can just make this arrow 2 or 4 or 6 or 8, all of a sudden CO2 levels outside this room won't keep going up? So this is part of a big thing that's going on in a lot of universities is what's called, you guys are studying, you guys are getting paid to study what are called natural climate solutions. If we can just figure out how to be slightly smarter in our grazing, we can improve soil health, but we can also cut back on the emissions of carbon dioxide, okay? So this is like a little bit of a high school intro, but I do this with all my college students and they all guess wrong. So this is very normal to not really understand. Question?
Yeah, you just quickly mentioned better grazing practices. Is there possibly you can indulge on that a little more?
Yeah, so let's do I know 3 words in Pekani. So here is the deal. I can erase some of this. So I want you to understand that this is what I'm going to call upland, and then we're going to go see it. And my word for upland is ispaco. Okay? And if you're like thinking I have a weird accent, it's true. I have a very weird accent. And then remember in here, like the floodplain, and it sort of extends over. I give Rio credit too. Like, when you get down into the low parts, which are going to be greener, these are usually browner and these are usually greener. This is the word that I learned for gooey ground. It's pak sikako. That stands for gooey ground, is what I've been told, or sikako. And the idea here is this is damp ground or gooey ground. And the idea with grazing for improved soil health is that we want to take places that are brown and we want to make them a little bit gooier, which means that what we're thinking about are things like, can we add snow fencing? So what does the snow fencing do? The snow fencing leads to an accumulation of snow, and then when the snow melts, unless you have a Chinook, right? The Chinooks basically eat the snow up. But if you have snow fencing accumulation, then what you can do is, these are going to be my soil particles, so we're way zoomed in. And if you have more snow fencing, maybe you have a little bit more water in between the soil particles. So that means we're going to have greener material like we do here if we put snow fencing up here on the upland. Does that make sense? The other thing that people have thought about is things like bale grazing. So we're doing winter feeding, for example, bale grazing. That's one idea. So we're going to be studying that. Another one that some people have thought about is doing prescribed burning. And I think we're sampling that next week during INI days out at the summer pasture. Another one is what's called high intensity rotational grazing. And the idea on high-intensity rotational grazing is that most of Montana looks like this. You have a big field, let's call it 100 acres. And what you do is you just let the cows wander wherever they want. 100 acres, or horses. You see a lot of horses up here in the Blackfeet Nation. And then the difference would be, what we're trying to do is take that, what some people have argued, and then you split this into lots of little pastures. You know, here I've got 8 little pastures, and you take all 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, and they all graze in here, but maybe they're only grazing in there for, 1 day, not 100 days. So this is 100 acres, 100 days, and then what you do is you basically have them go in there and really mow it down, but you're watching this really carefully. Some people are only doing it for 4 hours. It's really intense. And then you're like, oh my God, what a pain in the butt. Like you have to put up all this electric fence, yada, yada, and then you have to go move the cows, and what an incredible pain in the butt. Dude, the way it works now is you put these electronic collars, they're like shock collars on the cows, and then you get your little iPad and you draw the boundaries on the iPad, and basically you turn the cows over there, and you can train the cows that when they're walking towards an invisible fence, it gives them a little sound like, warning, you're getting close to electric fence. And then when they cross over it, and of course cows and bison love to go through fence, that's why fences was invented. But the big deal is that you can train them, and then you can move them all over in here, and then there, and then over there, such like that. So this is called high intensity rotational grazing. the Western science evidence to your question, Maverick, is not super, super strong. But what I'm just trying to show you is that we are part of a project where we think humans can be part of the solution. And again, remember, these two are in balance. These two are in balance. This one is not in balance. Even though it's small, it's the reason that 200 years ago, there was 280 parts per million of CO2 outside this room. And then today it's 420 parts per million. All of this huge increase comes from a really small arrow that's not balanced. Like right now, this is essentially zero. Like humans are not really working very hard on pulling CO2 out of the air. And then, hang on, I'm gonna give you my last word that I learned, which is CO2. You guys should memorize this. Otai sitma matu pani bokskoi. Okay, so you're like, wow, that's a lot of syllables in Piikani. So let me make sure I did this right. Otai sita matu. Otai sita, without the M, my bad. Otai sita matu pani bokskoi. So this, I was told from Colton Running Crane, you guys might know him. He's been helping me a little bit at Montana State University. He's like, I didn't know what to call carbon dioxide in Piikani, and so he calls this that which the plants eat. I love it. Does that make sense? You have to help me, Maverick. Anyway, this is all that I wanted to run you through in terms of introduction. It's already 1:40. I would love to walk out since I only have you until about 2:20. Quick question, Tucker? Any questions, JR? You guys have your arms up. Okay. Any questions? Because I think I just wanted to give you this introduction, and then we're going to go walk out, and I'm going to show you these holes right here at the crest, at the shoulder, at the shrub, down in the floodplain. I can't really show you that hole. It's covered with gravel now, but I can show you the creek. And what we'll try to do just in 40 minutes is a really quick walk. We'll go to the crest first, and then I'll walk you downhill, and I'll show you, 4 of those 5 holes. Does that make sense? For me, all Montana agriculture, because I'm not a farmer, I'm not a rancher, you guys would all starve if Tony was a farmer or rancher, because I would not be able to grow you enough food for us to eat. But I do get really excited. You witnessed it yesterday, teaching, right? And so one of the things that I like to teach about is if I were to pull out a chunk, oh, that's so funny. Chunk of this soil, like in general, what I handed you guys around yesterday was something that would have been a little bit similar to this, where it's very light, and when I rip it apart, you can see it's really, really dusty, right? I go like that, and my dust just flies away, so I'm trying to do this downwind of you guys. This implies to me, when I hand this around, it has a lot of organic matter, but it's not very wet, right? It makes sense. If we go into a big drought condition where it's not raining or it's not snowing, I know it can snow here in June, right? We're just not getting a lot of water into the soil. But what we walked over, do you see how it's green back there? So that's Depot Creek, right? What's happening is that Depot Creek gets snow melt from a huge area upslope, maybe all the way to Triple Divide Peak. I have no idea, right? I don't know where Depot Creek is born. But because it's funneling the water, do you guys get how it's browner here and it's greener over there? What we're trying to do in what we call the upland, I'm not going to pronounce it in Piikani, is make it a little bit wetter. We don't know how, but we know that some producers, right, who are just really curious, and you look like a high energy kind of guy, like you guys are going to do the experiments, and then what MSU and the interns can do is measure before and after. Or what we'd love to do is fence line contrast. So we do the brown side of the fence and the green side of the fence because we're trying to understand what's different. That's what makes me a really good faker, that I love soils, right? Is that there are some mysteries in there. The reason that we're here on this crest, and this hole was first dug in 2022, is that you can see that this chunk right here is much, much darker than this material right down here, right? If you can't see that color change, then we can have a little conversation. The reason this is darker here is organic matter. plants photosynthesize and they're pulling CO2 out of the air. They leak sugar into the soil and it makes it darker. This is lighter for two reasons. Not as much organic matter deep in the hole, and you can see our waste right here. It's much, much lighter, and you can even see these white spots. So we're actually picking up salts. This is such a dry part of the world. We can see the salts. We did the fizz testing yesterday, remember that? The question, as you go down here, I'm gonna show you two holes between here and the fence. My floodplain pit, which Kelsey guessed had the most carbon, and she was right. It has twice as much carbon in it as this hole right here. That sort of makes sense when you think about, oh right, the green line on the map, we have made that place a little bit wetter. It holds onto the carbon longer. That's the really important take-home message. And then we can talk about, I think we'll finish the tour. How's my timing, Jalen? Perfect. So we're gonna start walking towards that bridge, and we're gonna finish the tour hopefully in about 15 minutes at the bridge, and you'll see what's different about the creek, because we let the creek do the digging. Even though you guys are all great diggers, you showed that yesterday, we let the creek do the digging, and there's a 3-foot extent of where the creek has cut in, and you'll see it's relatively low in organic matter. I think that's partly because the creek is sort of exposing it to air, and it's not really as moist as when you go up just next to the gravel road that we walked across, where I can see clear evidence of beaver activity, right? So what beaver do, that's another trick, even on ranches, is that if you can get the beaver to hang out, meaning you're feeding them willows or something, like all of a sudden they can bring some of that water up into your soil and make it spongier and gooier. There are people who say that we should do beaver mimicry, right? So I think you guys will be working with Termaine a little bit, and I know just over there you can see just the faintest trace of Willow Creek coming down. There are some beaver mimicry structures on that. What that means is that humans are trying to do their best to fake that they're beaver. What's the difference between a beaver and a human though? Well, we have a little one that's sort of hidden. It doesn't go slap though, like when you're alarmed. What else is different? Who works harder? Beaver never stop working. They never stop working. You can pull their dams out and they'll be right back at it the minute that you're walking away after you pull out their dam. So let's go look at some of these other holes, and we'll end up down by the creek. So this is called the fence or the shrub pit, and I'm gonna show just Rio and Maverick what I'm talking about. So because of this cover, you know, we're in a little pocket right here. It ends up creating a microclimate. This is way more open because we've had people trampling and stuff, but just a little extra shade. This probably catches the snow a little bit better. All of a sudden, this is a much, much wetter place, and we see it in the surface. So this is what we're calling 38% organic matter. And you can tell it's organic matter because it just wants to blow away. But it's only a couple millimeters, and I don't have to go very deep, and I'm right back into all of the hard stuff. And so this one, on a 1-foot basis, does not have the most carbon. But I'll show you what does, which is underneath all that gravel. So we're supposed to be lined up. You can see the old T-post on the crest. We were just up on the crest. Some of you voted that that would have the most organic matter, but instead it's gonna be somewhere in here that has the most organic matter. The reason I'm stopping you right here is that one of the things that we're doing this summer and that you guys should be really excited about is you're gonna be putting sewer pipe in the ground. So that's like a 4 or 5 inch ring right there. And the reason that we put these sewer pipes in the ground is we want them to be really stable. And what we can do is we can actually measure the amount of carbon dioxide that's coming out of the ground. We would do that and we would call it a dry measurement. And then we'll put a plastic bag inside this. We'll fill it with 1 inch of water and we'll rip the bag out of the ring. And what will happen is that 1 inch of water will go down into the soil at a certain rate. And that certain rate really, really depends on how spongy and how much organic matter is in that soil. The more sponge you have, the better. And the faster that water will go down. Some people call it percolate, some people call it infiltrate. So we'll be measuring the infiltration rate. The reason we measure how much CO2 is coming out of it like right now when it's dry is that we're really excited after we do the infiltration test, which you guys will do on a future trip of ours, is what is the wet respiration rate? And it turns out if I were to measure this dry, I can't tell you the number off the top of my head. I mean, we've done it in the past with my graduate student. it might be some low number, right, of how much CO2. But as soon as you get the soil wet, it's like a party for the microbes. And they're going in there and they're starting to eat a lot more of the sugar, and you can have rates that are 10 to 20 to 30 times faster. So what we're really interested in, again, is this exchange of carbon dioxide between the land and the atmosphere, and how do humans make it lower, right? Because we want to produce less CO2 that's coming out of land so that we can all be part of the solution. Anyway, we have 2 infiltration rings set up. We're going to dig another hole right here. And then, Jalen, how much time do we have? 4 minutes. I thought it'd be 2 minutes. Let's go look at the last hole. I just want to read you these numbers that Tyler, my grad student, you met him yesterday, worked up, right? So from the top to the bottom, that T-post up there had 55 tons of carbon per acre foot. The Badger hole, that's our shoulder, 34, so a lot less. And then the shrub fence, remember it had that really light stuff on the right on the other side of the fence, that's 45. The floodplain that got, bless you, the floodplain that got covered with the gravel, 100. Like, it's not even close, the competition. And then finally, right here, we dug, let me find it, because we dug a little hole. There's a little scrape on the side. Let's find it. Yes, yes. So, yeah, we took samples right in here, and we went really deep, down to 3 feet. I don't want you guys to jump in there because you get totally wet. You can see it's all gooey. That is the definition of gooey ground. What we're trying to figure out, working with ranchers and farmers, is how do we get some of that gooiness way up there where it's super, super dry.